Hello again. I decided to record the last part so we make use of the time and you can study well over the weekend. First of all, I'd like to thank you for your attention. I'm not sure if it's nicer to study using e-learning or you miss the interaction in the classroom. However, I believe again that e-learning is quite effective. We will see from the result of the tests and the discussion forum. Make sure to follow my links and let me know if there is any unreadable material or any gap. Okay, I'm ready to record again and to simplify things again. Now in this chapter we talk about ozone loss, ozone hole, or mainly it is a hole but it is a loss in ozone. So we refer to it as a hole, but literally speaking it's not a hole per se, but it's the decrease in the level of ozone beyond the threshold and giving us a loss of O3. We will see why this loss is taking place. Is it naturally or anthropogenic? Is there any recovery? We hear about recovery of ozone, especially over the Antarctic pole. And we will see of strategies or ways that are being done in order to reduce this loss in ozone levels. The chapter is nice. It's short, 15 slides. And it's quite interesting, so hope you enjoy it and please communicate with me and we will get there with your help. Thank you, enjoy this chapter and hopefully we see each other on Tuesday. Let's get started. Ozone, where is it? Is it above the ozone hole? Where is it? Is it above the poles, above the equator? So the first ozone loss was found over the Antarctica, and this was quite recent, almost in the mid-20th century. This is quite interesting. So this raises the first question, is it really naturally made or anthropogenic? And environmental scientists believe that this is anthropogenic. Fine, here we can see an image back in 2006 taken by a satellite. Remember, we cannot take images of the stratosphere because the ozone is in the stratosphere, which is the second layer of the atmosphere. And remember, it stretches up to 36 kilometers. So this is where the loss is taking place, and from a satellite the area covered by the ozone loss is around 28 million kilometers square. The major benefit of the ozone is to block UV radiation. This was mentioned earlier in topic 5. It blocks the UV to penetrate. And we know that UV is harmful because it causes mutation, not only in human but also in aquatic and in different species, in terrestrial and aquatic species. How is ozone formed, O3? It is under the effect of the sun. The UV interacts with 3O2 to form 2O3. So it's 2O3. In general, O3 concentrations are much higher above the equator, and as the latitude decreases above the poles, the ozone level decreases. So diminish as the latitude increases. Okay? As I mentioned, over the South Pole, the Antarctica, the first ozone loss was significantly discovered back in 1985. And this was mainly during spring and early summer. So as if it is more likely to be discovered on a seasonal basis, and it's more towards spring and early summer. Why? Why do you think so? Remember, above the poles, the season, we have mainly 2 seasons, and the season is quite long, up to 6 months. So what happens that after a long winter period and cold, the gases will cluster together above the pole. The pollutants and the gases will cluster, and suddenly when the season shifts to summer or spring, then the sun will hit the gases, and here the gases will interact and there will be loss of the O3. Okay, so this is why it is dependent on the season, and mainly it is significant between the switch between winter, spring and early summer. Now, is it only above the Antarctica? Not really. Also above the Arctic it was discovered, above the North Pole, the Arctic. and so far the seasonal O3 loss is more above the North Pole than the has been lower than that over the South Pole. So the O3 loss is lower above the North Pole than the South Pole. Okay. So where is the hole larger than? Above the Antarctica. Let's have a look at the this image. We have here ozone in Dobson units. This is the unit of measurement of O3 above the pole. In orange indicates low concentration, and above 220 the concentration starts to increase as indicated by the blue light. When the blue light gets darker, then this means high concentration of ozone. We can see that orange color only occurs above the pole. This is the Antarctic pole. Now this is an animation of the ozone in 1993, and now it's extending 1994, and we can see it is varying. It's not a stable location or a stable concentration. The concentration varies based on the season and the year. This depends on the temperature, the annual temperature, the gas emission annually. We can see that there are periods where the concentration is less, let's say in 2005, then suddenly it increases. What about currently 2019? It stretches and it moves based on the current of the wind current of the gases, based on the temperature. So we are approaching, this is 2014, 15, it's moving, and we reach 17 less, 19, we are here. So yes, in 2019 it seems quite good, but look, this was back in 1981. It was barely seen traces of O3 loss beyond 220, so the threshold is 220. So it's a metaphor that we have again a hole. It's more than the loss, and more UV is penetrating because there's no block of O3. Now, why is this happening? And why do we know? I'm not sure if it had recorded this, but here we were seeing, if you visit earthobservatory.nasa.gov, we can see that back in 1981, O3 was barely seen, these traces of yellow, and in a blue, dark blue, we have enough O3 present. This is the satellite image. The O3 is measured in Dobson units, and when the O3 is beyond 220 Dobson unit, which is the threshold, then it will turn to be yellow and then orange. And we can see with the progress of time, this is back in 1979. In 1982 it was significantly, or it was discovered but significantly increased since then. And then with the progress of time, we can see that the loss is increasing. Okay, it is varying, however, and it fluctuates in size and location based on the season and based on the annual wind current and clustering of gases. So again, it's a metaphor. We don't have a hole per se, but rather than a loss in O3 level. And this loss should, if it is less than 220 Dobson unit, then we remark it as a hole. Okay. Now back to our slide. Here we see depleters of ozone. So which gases are most likely to deplete, and why do we know it is man-made or anthropogenic? The first depleter is CFC, which is the chlorofluorocarbon, CFC. And where do we find it? We find it in hairsprays, in air conditioners and refrigerators, foam blowing agents, certain agents that cause foam, cleaners for electronic parts, and sterilants for hospital instruments. So CFCs, they are very stable, they can persist in the air, it's a very stable gas, and it is odorless, cheap. This is why it is used non-toxic and non-flammable. Well, luckily, we will see in a while, it is banned and it is replaced or substituted by another gas. Other depleters include carbon tetrachloride, methyl chloroform, and methyl bromide. Carbon tetrachloride, this means 4 tetra 4 chloride with 1 carbon. It is a toxic solvent used as a sterilant in hospitals. Methyl chloroform used in cleaning as a cleaning solvent for clothes and adhesives, spray adhesives, dry cleaning sprays. And the fourth one, methyl bromide, which is used as fumigant. This means for pests, where firms or buildings, they are sprayed against pests, and these are stable and they are also depleters of ozone. Now what do we see here? It's quite interesting. Let's start with the sun. When the sun hits a CFC, so we see the C in the center, carbon, F, fluorine, and chloride around it. When the sun hits it, Cl is stripped out. Now it is free. It has to attack something. It attacks the O3, as we see it here. When it attacks O3, it forms ClO, and O2 is removed. And the O3 then is damaged into O2 and O, and ClO. This is how O3 is damaged, okay? And interestingly, each Cl can destroy up to 100,000 O3 molecules. So it goes in the cycle back again, stripping up to 100,000 O3 molecules. And this is why it is completely banned. It's very stable. The other molecules, they work similarly by releasing their Cl or their stable atom and destroying or stealing an O from O3. Okay, here again we see Antarctic and Arctic. We see that the Antarctic, which is the North Pole, the South Pole has a larger hole, okay? Health problems. Why should we be concerned? As we mentioned, more UV is hitting the troposphere, more mutation at the level of the skin, more skin cancer. Also, it might damage the eye, forming cataracts, and it might suppress the immune system, leading to susceptibility to infections and other cancer. Here we can see that the UV has UVA and UVB. They can penetrate the skin and reaching the cells, the inner cells, and causing damages. And this is a normal eye versus an eye cataract. We see that there is like a cloud, white cloud. This is a mole. It is changing the shape of it. It becomes asymmetric. It starts to grow, this mole, and as a result it becomes melanoma. This is a skin cancer caused by UV. In addition, we have economic and environmental problems. So economic problems, it might lead to loss in the growth of crops, field crops and agriculture. Photosynthesis also might be affected, and we have corrosion of paints and plastics and degradation of outdoor material. How can we protect the ozone layer? There are different summits that are taking place in order to phase out the use of these ozone depleters, so by banning their use or by replacing them. Example, CFC have been replaced by HCFC. HCFC is less stable, and a lot of countries, they are working and in setting certain threshold to lower the levels. Now, can we go back to reset or to a pre-level, pre-1980 level? Well, scientists do not believe so. We cannot return back, and if we reach certain levels that are quite promising, this would be not before the mid-21st century, almost 2050. CFC production, as we expect, is more released by developing countries or industrialized countries in blue, and less by developing countries. However, the projection that CFP is decreasing, and we can see there is a significant decrease in CFC use. How can we protect the ozone layer? We need to make sure so certain summits are being held annually in order to reimburse developing countries for the cost of complying with the international protocol. So if they replace the cheap products by more expensive products, these can be reimbursed by developed countries. And there are global cooperation to prevent the potential global disaster. That's it. It's quite easy. Have a look if the ozone hole have recovered in 2019, and leave your comments on WhatsApp, on discussion forum, and also take the test your knowledge quiz. Bye for now.